Hi, so welcome to today's class, and in today's lesson, we want to learn the difference between mass and weight. So I will listen at a couple of differences between mass and weight and the reason why they are actually different. So what is mass actually? So the mass of a body is the measure is the measure of is the measure of quantity is the measure of quantity of the material in the body. Quantity of material in the body. So how much material the body has, we talk about, that's the mass. Now, and one thing about the mass is that the mass is constant everywhere. It is constant everywhere. It doesn't change. The mass does not change. It's the same everywhere. It doesn't change. It's the same everywhere. So, and mass is actually a measure of quantity of material in the body. So how much quantity of material that the body has is what we tend to mean by mass. So if you look at a yam, two different yams, you say, why is this one more massive than this one? It's because the heavier one contains more yam material than the other one. Okay, so let's look at what weight is. Let's look at the definition of weight. So weight itself, weight is actually weight weight is the force of gravity, the force of gravity on the body. So the force of gravity on the body. Remember that force of gravity is acting downwards. Force of gravity is acting downwards. Let me draw that very. I'm very bad in drawing. Pardon me. So force of gravity is acting downward. So remember that this object would have a mass. So that means that the force of gravity is acting downward. That's G. Then the object has a mass. So what's going to be the weight? The weight has to be, since it is force and it's a weight is the force. So, and what is the formula for force? The formula of force is F equals to mass times acceleration. Now, and this G is actually called acceleration that is due to gravity. Acceleration due to gravity. Okay, so that this is G and it's the acceleration due to gravity. So that would be mass M. Acceleration that is due to gravity is going to be G in this case, and that gives us W, the weight. So the weight is calculated as W equals mg. Now let's talk about the properties of acceleration due to gravity. Let's talk a bit about acceleration due to gravity. Acceleration due to gravity. Let's talk about that for a minute. Now the acceleration. Now we have the Earth. The Earth. Okay, let's say this is the Earth. Now, if you notice that this sphere is not perfectly a circle, it's not a perfect sphere. It's just this place is this place is slightly longer than this place. So that is slightly longer, and the circle at this point, this center, is actually called the equator. Let me do that again. The circle at this point is actually called the equator. Okay, good. So now, and this is called the pole. Let me draw that again. So that's this. This is the pole. So you have the North Pole and the South Pole. This is the North Pole and this is the South Pole. Okay, of the Earth. So now, what they're saying is that, what I'm trying to explain is that at the pole, either here, either at the North Pole or at the South Pole. Now, the acceleration due to gravity is the greatest there. So that's why you have the greatest G, acceleration due to gravity. Now, at the equator here, it is where you have the lowest acceleration due to gravity. So that's why you have the lowest G. So at the pole, either north or south, you have the greatest G, the greatest acceleration due to gravity. And at the equator, you have the lowest G. And why is it like that? Why it is like that is because if you see the diagram I drew before, this diagram, you notice that this circle is slightly flattened at the equator. So this place is slightly flattened at the equator. So it compresses like it compresses. So this circle on the equator is greater than the circle. The circle on the equator is greater than the circle of the pole. And what does that mean? That means if this is the center of the Earth, then the radius of the equator is greater than the radius of the pole. So that means the distance from the center of the Earth to the equator, any point on the equator, is actually greater. And one thing about acceleration due to gravity is that the further you have from the influence of gravity, the less value of gravity, the less impact gravity has on you. So that means if you are very close to the influence of, if this is where gravity is acting, and you're very close to gravity will have more pull on you. But if you are far away from the source of gravity, then the gravity has less pull on you. So that means at the equator, because it has more distance away from the center of the Earth, which is the source of gravity, the G is less. Then the pole, which is closer to the center of the center of the Earth, which is the source of gravity, is going to have the greatest G. So that's why you have the lowest and the greatest G. And then one other thing I want to talk about with is that if you take an object away from this from the influence of the Earth, and you take it to some other planet, or let's say the moon, you take it to the moon. Now, G will be different on the moon. Acceleration due to gravity is different on the moon. Why? Or any other planet. It's different from, I think the Earth is about between 9.8 meters per second squared to 10 meters per second squared. So that's the range for acceleration due to gravity on the Earth. But anywhere in the other planet is different. from this value. So in the earth is in the moon, on the moon is lower than this, about 3 point something, I can't really remember, but about 3 point. So it's lower than the associated gravity of the earth. Now, so let me just say what actually causes gravity. So it's actually the mass of the thing that causes gravity. The mass of the astronomical body that actually causes gravity. So remember that the mass of earth is greater than the mass of the moon. So if the mass of the earth is greater than the mass of the moon, then acceleration due to gravity on the earth must be greater than acceleration due to gravity on the moon. So you get the idea. So what about if you are on Jupiter? Of course, Jupiter is bigger than Earth. So that means since the mass of Jupiter is greater than the mass of the Earth, then the acceleration due to gravity in Jupiter must be greater than the acceleration due to gravity on the Earth. So you see, so that means mass has to do with gravity. So the more massive an astronomical body is, the more acceleration due to gravity it has. So and if you take an object away from the earth where it has about 10 meters per second squared acceleration due to gravity on the earth, you take it to the moon. Of course, let's say you have the mass of that object is about 5 kg. What's going to be the weight on the earth? The weight on the earth is about 5 m times g, 5 times 10, that's about 50 newtons. That's about 50 newtons. Take it to the moon. So that means since the acceleration due to gravity is changing, and of course the earth is greater than the gravity on the moon, and the gravity of the moon is about 3 point something, so 5 times 3 is about 15 newtons. So you have approximately 15 newtons. That's the weight on the moon. So you see that it's different. On Jupiter it's going to be greater because that will be greater than 10. So on Jupiter is greater than the acceleration due to gravity on the earth. So in Jupiter the weight is going to be about more than 50%, so it's going to be greater than 50 newtons. So you can see that weight changes depending on where you are measuring the weight from, but the mass remains the same. You can see 5 kg, 5 kg, 5 kg. It remains the same, but the weight changes, and it is as a result of the acceleration due to gravity of the place that you are taking your measurement from. So mass doesn't change and weight changes.